So Chapter 3, Part A. So we're going to look at the structure and properties of ionic and covalent compounds. In Chapter 2, we focused a lot on valence electrons. So valence electrons were the electrons in the outermost shell of an atom. These are the electrons that are available for bonding. So a chemical bond, by definition, is interaction between these valence electrons. This could be through transfer of electrons, or it could be through sharing, as shown in the picture here. The two types of bonds we're going to talk about this chapter are ionic bonds and covalent bonds. So ionic bonds are when electrons are being transferred. And we looked at this in Chapter 2. So when a neutral element either gains or loses an electron, you get an ion. So ionic bonds are results when the ions themselves are attracted to each other. For instance, if you have one element transferring or giving up an electron to another, what's going to happen is you're going to form a cation, a positively charged ion that has lost an electron, and an anion, which is a negatively charged ion that has gained an electron. So now you have a positive and a negative charge. And what we know of opposites charges is they attract. So ionic bonding is the transfer of electrons, and the resulting ions are now attracted to each other due to their opposite charges. Next, let's look at covalent bonding. So covalent bonding is not a transfer. This is when electrons are shared. We have two types of covalent bonding. We're going to look at nonpolar covalent and polar covalent. So what nonpolar covalent is when the atoms involved are sharing those electrons equally. For a polar covalent bond, this is when the atoms involved in the bond have an unequal sharing. What that means is one atom wants those electrons more. So they're not going to share them as much. This is going to result in one atom having a slightly positive charge, and the other atom, the atom that wants the electrons more, having a slightly negative charge. So let's first focus on ionic compounds, and we'll come back to covalent in a moment. So for ionic compounds, we said they're composed of ions. Ions being charged particles that form when an atom gains or loses an electron. Typically, this occurs between a metal and a non-metal. If you'll remember from Chapter 2, we saw when we were looking at ions that metals like to lose electrons, and so they form a cation, a positively charged ion. The nonmetals, on the right side of the periodic table, like to gain electrons. So if they gain electrons, they become negative, resulting in an anion. Well, since opposites attract, it would make sense that the cations and anions are attracted to each other, creating an ionic bond. So most often than not, we'll see metals and nonmetals forming ionic bonds. Now the bond is actually created due to the electrostatic forces between those positive and negative ions. In the example below, you can see the sodium atom, and all that is shown is the valence shell, the outermost shell. Notice there's just one electron in that shell. Well, that is due to the fact that sodium is an alkali metal, and all alkali metals have just one valence electron. So what happens is that sodium atom loses that one valence electron to another atom, in this case chlorine. The reason sodium wants to lose an atom is because it wants a full octet. So by getting rid of that one atom, it will now be in a noble gas state and be happy. Well, let's look at chlorine. So chlorine is the atom that's going to receive that electron from sodium. We're once again showing only the valence shell of the chlorine atom. You can see, if you count the electrons, that there are 7 green electrons in the valence shell. Now these 7 electrons, we can see from the periodic table that since chlorine is a halogen, all halogens have 7 valence electrons. Remember, everybody wants an octet. Everybody wants 8, just like the noble gases. And so, when sodium loses that electron and gives it to chlorine, that completes chlorine's octet, and now you can see The chlorine has 8 electrons, so it has a full outer shell and it is now happy. Since chlorine gained an extra electron, it now has a -1 charge. Since sodium lost 1 electron, it now has a +1 charge. So these opposite charges are attracted to each other, creating an ionic bond. Let's look at covalent compounds. Covalent compounds, we said, were when elements or atoms share electrons. So there's no transfer. There's no positives and minuses. So you can see in this first picture here, we have 2 atoms coming together. And in this circle here is them sharing their valence electrons. So with covalent bonds, the atoms themselves need to be in much closer proximity to one another. Now, there's 2 types of covalent bond. We mentioned that there was a nonpolar and a polar. So the nonpolar is equal sharing, and that's what you see in these diagrams to the right. You can see that the electrons are placed in the center between the 2 nuclei. Polar covalent bond would be where one atom has the electrons closer to its nucleus than the other, meaning it wants it more. It's a more electronegative atom. So let's look at an example of that. So in the diagram below, I have shown nonpolar covalent, which is the first example in blue here, polar covalent, second example in green, and then of course an ionic bond in red. So I have the different stages. So looking at a covalent bond, notice, so we have 2 elements, X and X. There is a pair of electrons right between them that they are sharing. Now this blue egg shape around them is the electron cloud, and notice it's very symmetrical because they are sharing those electrons equally. It is a nonpolar covalent bond. However, sometimes they don't share the electrons equally. So in the next picture, we have a polar covalent bond. Notice we have X on one side and another atom, Y, on the other. Now notice where the electrons are this time. They're still sharing, we can see, because of this egg-shaped green sphere here, but it's not quite equal, it's not symmetrical. That's because, if you notice, the electrons are closer to the Y atom. Why? Because the Y atom wants it more. The Y atom is more electronegative, so it pulls the electrons closer to it instead of sharing them equally. That's why you'll notice up top there's this little delta negative by the Y atom. What that delta sign means is partial. So it's partially negative on the Y side, making the X atom partially positive because it's not sharing those electrons equally. Now going to the other extreme, an ionic bond, notice there's a separation between that cloud. They're not sharing. They have fully transferred. So the Y atom has a negative charge and has both electrons to itself. The X atom has a positive charge because it gave an electron away. So how are we going to figure out the difference between a nonpolar covalent and a polar covalent bond? We can use the periodic table to predict electronegativity, and you'll actually get an electronegativity table which you can use the values to calculate. Here's that electronegativity table that I was referring to on the previous slide. So you can see it looks like a normal periodic table with the element symbols. However, underneath each element symbol are numbers that are not the mass number. So what these numbers are the electronegativities of each element on the periodic table. So we're going to use these to try to figure out whether a compound is polar or nonpolar. So to do that, we're going to use this equation here. So delta En is equal to, and those are absolute value bars, just like when we do our percent error calculation. We have En1 minus En2. So what this means is that delta En means change in electronegativity. Whenever you see a delta sign, it means change in. So to figure out the change in anything, you always need to take the final minus the initial. So what we're doing to calculate that is taking the electronegativity of one of the elements involved in the bond and subtract it from the electronegativity of the other element present in the bond. So an example, say we wanted to calculate the electronegativity of a boron-hydrogen bond. So we would find boron on our table and see that it has an electronegativity value of 2.04. We then would find hydrogen and see that it has an electronegativity of 2.20. Subtracting those from each other, we would get a negative number, but since we have the absolute values bars, we change that to a positive. So 0.16 would be the change in electronegativity. So what do we do with that number? We compare it to the scale shown here. So if the change in electronegativity falls between 0 and 0.5, it can be classified as a nonpolar covalent bond. In this case, the boron-hydrogen bond does fall in that range. It's 0.16. So it's less than 0.5 but greater than 0. So this would be a nonpolar covalent bond. If it was higher than 0.5, so between 0.5 and 1.9, it would be classified as a polar covalent bond because that's a much wider difference between its electronegativities. In order to get a polar covalent bond, this only occurs when we have two different atoms that have a large difference in their electronegativities, making one atom much more electronegative, thus wanting those electrons a lot more than the other atom. Notice we can do this calculation for ionic bonds as well. Generally, when we see a metal and a nonmetal, we classify that as an ionic bond. But some metal-nonmetal bonds can be classified as polar covalent using this calculation. So now we're going to look at formulas. So formulas are combinations of symbols giving the type and the number of atoms. Often going to refer to compounds as binary, sometimes tertiary, so on and so forth. So what binary compound means is when you have two different elements combined. So here are some examples of some formulas. In this first one, we have NaCl. So there are two elements present, sodium and chlorine. Now, the subscripts present on these chemical formulas indicate the number of atoms. But notice, for this first one, NaCl, there are no subscripts. So if you don't see a subscript, you can assume there's just one of each of those atoms. So this chemical formula tells me there's one sodium and one chlorine. Looking at the next example, we have CH4, once again a binary compound. This would be carbon and hydrogen together. We use the subscripts to figure out how many atoms of each element are present in the compound. So carbon doesn't have a subscript, so we know there's just one carbon. But after hydrogen, we see this subscript of 4. So that means there are 4 hydrogens for every one carbon in this compound. The last example has 3 elements now. We have carbon, hydrogen, and oxygen. Once again, to figure out how many of each, we're looking at the subscripts. So 5 carbons, 12 hydrogens, and 2 oxygens. So now let's look at covalent compounds. So we're going to learn how to name them. So a covalent compound is a nonmetal with a nonmetal. So notice my nice color-coded periodic table with the nonmetals being in yellow. Once in a while, we will see covalent compounds between a semimetal and a nonmetal. So just be aware of that. It's not always just nonmetals. That's just the most common type. When we find a covalent compound, it's when the electrons are shared. Sometimes they're shared equally, sometimes not so equally. Covalent compounds are also often referred to as molecules. So when you hear the term molecules, we're talking about covalent, not ionic compounds. So how do you figure out, based off the chemical formula, if a compound is covalent or not? Well, find the elements present in said compound and see where they are on the periodic table. So nitrogen, for instance. Nitrogen in yellow here is a nonmetal. It is combined with oxygen. Oxygen right next door to him, also a nonmetal. So now, since we know we have two nonmetals, we know it's covalent. So why is it important to know if a compound is covalent or ionic when you're trying to name it? Well, there's different rules for naming covalent compounds than there is for ionic. With covalent compounds, you start by naming the first element. So in the example we just saw, N2O5, you would start by writing nitrogen. Then you find the second element present and name that one as well. But the second element isn't going to be oxygen. We're going to add an ending to the second element present, and that ending is going to be an IDE ending. You can see off to the right here is a table of how most of the nonmetals change when an IDE is added. For instance, we're looking at this nitrogen-oxygen compound. So when we add an IDE to oxygen, it doesn't become oxygenide. It actually becomes oxide. Same with nitrogen. If we needed to add an IDE ending to that, if it was the second element present, it would become nitride, not nitrogenide. So just be aware of that. Next, we need to add prefixes to indicate how many atoms of each type are present. So this is where the subscripts are going to come in handy. Looking at the prefixes, off to the right, I have them labeled 1 through 10. In this course, we won't see higher than 10 when we're actually naming a covalent compound anyway. So in the case of the example above, since there are two nitrogens, we would label that as dinitrogen. For the oxygen portion, since there are 5 of them, we would look at the prefix 5 and it would be called pentaoxide. So dinitrogen pentoxide. The correct name for that covalent compound. Now there are common names for a lot of the covalent compounds that we will be naming, but we're going to try to systematically name them. Let's try another example, CO2. Start by naming the first element. So C is carbon. Second step, name the second element, but add an IDE ending to it. So the second element is oxygen, so oxygen becomes oxide. Last but not least, we're going to add prefixes to each to indicate how many atoms. So carbon, there is no subscript after it, so we assume there's just one carbon atom. The subscript of 1 tells us it should be mono. For oxygen, there are 2, so in front of the oxide portion, we would write di. So we come up with monocarbon dioxide. Now, if you think about it, that doesn't quite sound right, because I'm sure many of you have heard of carbon dioxide, but never of monocarbon dioxide. So this is where we get our first exception. There's always exceptions to every rule. The exception is that the prefix can be dropped on the first element if there's just one, if it's mono. Okay, so what that means, if there's only one atom of the first element in that chemical formula, you do not put the prefix. You do always need the prefix on the second element, and you will need the prefix always on the first for numbers 2 on up. So Next, we're going to look at Cl2O7. So let's systematically go through it. Cl is chlorine, so that would be our first word, our first element. Second element, oxygen. Since it's a second element, we would change it to oxide. Next, add prefixes. 2 chlorines would be dichlorine. 7 oxygens would be heptaoxide. So dichlorine heptaoxide. Now notice it looks a little weird having two vowels right next to each other. So another rule, and this is just a spelling error, which I won't ever count you off for because I'm not the best speller myself, but if you have two vowels next to each other, an A and an O or an O and an O, it is just changed to O for the spelling purposes. It would just become heptoxide. Now let's practice with some more examples. pH3. Go ahead and pause if you want to try to come up with it on your own. I'm going to work through these kind of quickly. So pH3, we have phosphorus and we have hydrogen. Hydrogen being the second element present, so it's going to become hydride. Next, we look at our prefixes. So you can see at the top here, we have the basic outline of how we name these. We have a prefix, the element name for the first atom present, and then prefix, and the second element has an IDE ending. So in this case, there's only one phosphorus, so you might start to say, oh, it's monophosphorus. But remember that rule. If there's only one of the first element present, you don't put the mono on it. So it's not going to be monophosphorus, it's just going to be phosphorus. The second element present, hydrogen, will be tri, because there's three of them, hydride. The next example, so there are two nitrogens, so the prefix is going to be di-nitrogen. The second element, present oxygen, there are three, so it would be tri, and then oxide for that IDE ending. Notice the IDE ending is only on the second element present. Another example, SCl6. So S is sulfur. How many? There's just one. Since it's the first element present, we are not going to use the prefix mono. So it will be sulfur, and then chlorine becomes chloride. Since there are 6 of them, the prefix going on that one will be hexa, so hexachloride. Now let's look at writing formulas of covalent compounds. So given the chemical formula, like we just saw in the previous slide, you need to be able to name the compound. However, you also need to go reverse. What I mean by that is if you are given the name, you need to be able to write the corresponding chemical formula. So let's look at an example. If you were given the name dinitrogen tetroxide, how would you figure out what the chemical formula is? Well, you can use the element name portion, nitrogen, and oxide to figure out the elements involved. So nitrogen has the symbol N. So you would look it up on the periodic table and see what its symbol is. Oxide, that's just the IDE form of oxygen. And when you look up oxygen on the periodic table, its chemical symbol is an O. So now that we have the chemical symbols, we just need to put them together with the prefixes involved. So what the prefixes are going to tell us are how many atoms of that element are present in the chemical formula. The prefix of di in front of nitrogen tells me there are 2 nitrogens. The prefix tetra in front of oxide tells me there are 4 oxygens. So putting that together, we get N2O4. So next, let's look at ionic compounds. Ionic compounds are usually a metal with a nonmetal. We'll explore a little bit further and talk about polyatomics and some other combinations that form ionic compounds. They're always charged components. Remember when we talked about ionic compounds, we said that they were formed because of ions, right? Transfer of electrons. So when you're approaching a chemical formula, how do you identify it as an ionic compound? Well, if you're looking at the periodic table, I'm not talking about polyatomic ions, you just look at the elements present in the formula. So we have calcium, which is an alkaline earth metal in that fuchsia or pink color. And then we have that attached to chlorine in this chemical formula. And chlorine is a halogen, so it's way over in the nonmetal portion. So metal in a nonmetal, that tells me it's ionic. When it's ionic, I have a different way to name them. So I'm no longer going to be using prefixes if the compound in question is ionic. So how do you name ionic compounds? Well, of course you have to start by figuring out if the bonds are ionic or not. And we just looked at how to do that. If they are ionic, we need to see, well, are there polyatomic ions involved? We also need to ask ourselves, are the metals involved, do they have multiple charges? Meaning, are transition metals involved? So ionic compounds can become very difficult to name because there's a lot of metals on the periodic table to take into consideration. But we're going to start out slow with a standard naming system for binary compounds. Remember that word binary means 2 elements only. Then we'll move on to talk about polyatomics and the transition metals. Let's look at naming binary ionic compounds. If you look at the 3 examples above, you know that all of them are ionic because we always have a metal with a nonmetal. Also notice, the metal always comes first. So we have sodium, an alkali metal, the first element present in the first compound. We have magnesium, which is an alkaline earth metal, and then potassium. So it's always metal and then the nonmetal portion. We are not going to use prefixes, so forget about them. No mono, di, tri, tetra, anything. When we name them, we're simply going to take the first element, straight off the periodic table, no special ending. That's going to be the metal portion, the cationic portion, the positive ion. Then the second element present, which is the nonmetal, we're going to put the element name with just an IDE ending. So we are still going to use IDE endings like we did for covalent, but we're not going to use a prefix. Now the nonmetal portion is usually the anion because they gained an electron from the metal portion, making them negative. So here is the basic systematic naming. You name the positive ion first, which is most often a metal, not always, but most often. The second element present, the negative portion, you use its name, but with an IDE ending. So let's start out with NaCl. The metal portion is sodium. So you would just find that on the periodic table and write the name exactly how it appears on the table. For the second portion, it's chlorine. And since it's the negative ion and the second one present, we're going to add an IDE ending to that to become chloride. Next, we have Li2O. Now notice there are 2 lithiums, but does this matter? Well, it matters in the sense that yes, there are 2 of them, but it doesn't matter for naming purposes. We're not going to be using prefixes, no di, tri, nothing like that. So instead, we just look at the symbol, in this case Li, realize it's lithium, write that name down. The second element present, oxygen, will have an IDE ending and become oxide. KBr, finding K on the periodic table, is potassium. Then we have bromine, which becomes bromide. Last but not least, Ca, calcium. Cl, chlorine, but since it's the second element present, chlorine becomes chloride. Notice there are 2 chlorines, but we didn't say dichloride. Now let's look at going the reverse way, much like we did with the covalent compounds. So we're going to be writing chemical formulas based off of the name. So it's a little more difficult with ionic compounds to take the name of the ionic compound and come up with the formula. Because since we aren't using prefixes, it doesn't tell us how many atoms of each we need to put. So how do we figure it out? Well, we can figure it out because we know what charges the main group metals form in ionic compounds. Those are listed in the periodic table to the left. So how you would start this, if I'm giving the compound magnesium bromide, what I would do is I would find both magnesium and bromine on the periodic table and write down their corresponding charges. Magnesium is an alkaline earth metal. Notice it's going to form a +2 when it's an ionic compound. So I write magnesium with a 2+. So what ion does bromine form? Well, it's a halogen, so it's going to form a -1 ion by gaining 1 electron. Next, what I need to do is make the compound neutral. What does that mean? Well, magnesium bromide is an ionic compound, yes, but the compound itself overall is neutral. And if I had just one magnesium and one bromine, that would not make a neutral compound because I have a +2 charge and a -1 charge. If I add those together, it's not going to equal 0. So what do I need? I need another bromine. If I add another bromine, now I have 2 -1 charges, which would give me a total of -2. That is going to neutralize my +2 charge, which is on the magnesium. So my compound would be Mg1Br2. I would need 2 bromines to neutralize the +2 on the magnesium. Another way to do this is called the crisscross method. So how do we use the crisscross method? We start off the same way. We take the name of the compound. In this case, we're using aluminum oxide as an example. You would start by finding the chemical symbols and the charges of both aluminum and oxygen. So aluminum has a +3 charge. Oxygen, being in group 16 and having 6 valence electrons, will want to gain 2 more to become a -2 charge. So how does this work? Well, you take the number, so this +3 on aluminum, and that 3 is going to become a subscript on oxygen. The 2 on oxygen, not the charge, just the number, is going to become a subscript after aluminum. So we're crisscrossing those numbers. So the formula that we're going to get is going to be Al2O3. The 2 coming from the charge on oxygen and the 3 coming from the charge on aluminum. Notice we just brought the numbers, not the charges themselves, so we left the positives and negatives alone. What that means is I need 2 aluminums for every 3 oxygens in this compound. What we're showing here is just that the method does work and that it is a neutral compound. So we just said we have 2 atoms of aluminum. Each of those atoms has a +3 charge. Given this chemical formula, that subscript of 3 says that we have 3 oxygen atoms, and we know that each of those oxygen atoms are going to have a -2 charge. So what we're trying to check is that it is indeed neutral. So if we have 2 atoms of aluminum at a +3, that's going to give me +6 on the plus column side. I have 3 atoms of oxygen, each with a -2, so that's going to give me a -6 on the oxygen column. A +6 plus a -6, they cancel each other out. That compound is overall neutral. When you are using the crisscross method, you do need to make sure that you're using the smallest whole number ratio. So if you can simplify it down, do so. I'll be showing some examples in class where you'll see this. Example shown here is if I took calcium, which has a +2 charge, and oxygen, which has a -2 charge. Now, if I do the crisscross method, I get Ca2O2. Well, notice this can be reduced down further. If I divide both by 2, I will simplify it to just CaO, where I have 1 calcium per every 1 oxygen atom. So now let's look at naming ionic compounds if a polyatomic ion is involved. And in order to do that, we need to know what a polyatomic ion is. So polyatomic ions are ions, meaning charged components, charged compounds, that consist of two or more atoms. Now, the atoms in the polyatomic ions are bonded covalently, but the polyatomic ion itself has an overall charge, whether it be a positive or a negative charge. Since it has a positive or negative charge, it is used as either a cation or an anion in ionic compounds. So off to the right here, I have a list of common polyatomic ions that we'll see present in some of the compounds we're going to be naming. I do want to point out that most of them are negatively charged, or anions, so they're often going to take the place of the nonmetal portion. There is one on this table that has a positive charge, NH4+. That is the ammonium ion. So since it has a positive charge, it's going to take the place of the metal portion, the cationic portion of the ionic compounds we've been naming so far. Another thing I want to point out is a lot of these names are similar. So let's look at the last two in the table. We have SO4 with a 2- and SO3 with a 2-. So notice they only differ by one oxygen. When you're looking at their names, the names themselves, sulfate for SO4 and sulfite for SO3, only differ by one letter. So be very careful when you're naming these compounds, because even just one letter difference or one oxygen difference can make the answer go from right to wrong. Let's look at some examples. When we name these, we're going to be naming them just like binary ionic compounds. We're going to start with the cation portion, and we'll name that straight from the periodic table. Now with the anion portion, the polyatomic portion, we'll find the polyatomic ion on the table and use the name given on the table. So we're not going to add any IDE endings when a polyatomic ion is involved. So how do you know if a polyatomic ion is involved? Well, looking at this first example, I would know one's involved because there's more than 2 elements present. I have Sr, strontium, I have carbon, and I have oxygen. So I have 3 elements present. So that must mean there's a polyatomic involved somewhere. So the Sr portion, strontium, we would find that on the periodic table and just write its name exactly how it is on the periodic table. The rest of it, the CO3, we would look it up in the polyatomic table, see that CO3 has the name carbonate, and write that name down. So strontium carbonate would be the correct name for that polyatomic ionic compound. Let's try a few more. So another clue showing that an ionic compound has a polyatomic in it is if there's parentheses. So whenever you see parentheses around it, that means that that is a polyatomic. The number outside of the parentheses is saying how many of that polyatomic ion are present. In this case, 2. So how do we name it? Start with the metal portion, strontium. NO3 being a polyatomic we would find on the table, and NO3 has the name of nitrate. Does it matter that there is 2 of them? No, because this is an ionic compound and we're not using prefixes. Next we have Al2SO4 sub 3. Once again, parentheses alert me to the fact that there's a polyatomic involved. So Al is aluminum, SO4 we would find on the table, and it is sulfate. So the name for that compound would be aluminum sulfate. Now in this next example, you might notice at first that there's no metals. Another thing you might notice is that there are 4 different compounds listed, or 4 different elements listed, excuse me. So since there's no metal, that gives me a clue that this first part is probably a polyatomic, and it is. It's our only positive polyatomic on this table, ammonium. When you're naming a compound with 2 polyatomics, simply write both names down, starting with the first one present. So this would be ammonium, and then the NO3 portion, nitrate. Here are some more examples. Now we're going to take the names of ionic compounds and come up with the chemical formulas. Now, we looked at that already with the magnesium bromide example and the aluminum oxide example. So whenever you're approaching a problem like this, the first thing you want to do is find the element symbol of both atoms or polyatomics involved and their charges. So what I have shown here is the first step. I have written down both elements involved in each example along with their charges. Notice when we get to the polyatomics. How do I know it's a polyatomic? Well, the first three examples have IDE endings. That's because when we name binary ionic compounds, we add an IDE ending to the second element present. So I know that nitride is really just nitrogen. Bromide is really just bromine. However, the last two examples, I have an ATE ending. So this alerts me to the fact that it's probably a polyatomic. So I would look at the polyatomic table, find nitrate, and write it down exactly how it appears, NO3 with a -1 charge. Same with sulfate. Well, now how do you come up with the chemical formulas? You can do the crisscross method, or you can line them up until the charges cancel and the element is neutral. For instance, this first one, potassium has a +1, chlorine has a -1. Do those charges cancel? Yes, they do. So what that means is I only need one of each to make a neutral compound, so my formula would be KCl. Now I'm going to skip down to aluminum sulfate, the last example, because I'll work on these during class. With aluminum sulfate, I'm going to use the crisscross method this time. So I have 3+ charge on aluminum and a 2- charge on the sulfate. So how do I come up with the chemical formula? That 3 is going to become a subscript on the SO4. The 2 is going to become a subscript on aluminum. So I'm going to get Al2 and then SO4 sub 3. Now the trick with polyatomics is if I have more than one of them, I want to make sure to put parentheses around that entire polyatomic, and then I'm going to put the 3 on the outside of those parentheses. We'll work on more of these in class. Now it's time to look at the last type of ionic naming compounds. So it's the stock naming system, and this is with transition metals. So far, all of the examples that we've looked at have been with main group metals. We've been using alkali metals, alkaline earth metals, and aluminum. Now we're going to look at the D block, the transition metals. So all of those numbers in blue, all of those elements in blue. So all transition metals have variable charges. What that means is we can't predict what its charge is based off of where it is on the periodic table. For instance, iron, it can have a +2 charge or a +3. Copper can have a +1 or a +2. Cobalt, a +2 or a +3. There's no rhyme or reason to it just by glancing at the periodic table. There's a deeper way to figure this out. So how are we going to figure it out? Well, given this example, FeCl3. So I would identify that as an ionic compound because iron's a metal and chlorine is a nonmetal. But I can't just name it iron chloride and be done with it. Why? Because the metal involved is a transition metal. And since the transition metals can have multiple different charges, I need to somehow indicate when I'm naming it which ion it is. Is it the +2 iron or is it the +3 iron? So how do I do that? I do that by using Roman numerals. So if, for instance, this is the +2 ion of iron, I would write iron and then Roman numeral 2. If it is the iron 3+ ion, I would write iron and a Roman numeral 3. So how do we figure out which ion it is just by looking at the chemical formula? Well, you're going to start with the one you know. So we just said, I don't know what iron is. What is the charge on it? Is iron +2 or is it iron +3? Okay, well, since I don't know what the charge is on that, let's look at what it's attached to, what it's bonded with. So this iron is bonded with chlorine. And I do know what the charge on chlorine is. Chlorine's a halogen. It's number 17 here. And halogens always have a -1 charge. So if I know that chlorine has a -1 charge, well, how many chlorines do I have? The subscript tells me that. I have 3 chlorines. So what's the total negative charge that I have? Those 3 chlorines tell me I have a total charge of -3. So what I need is for this chemical formula, this compound, to be neutral. I know it's neutral because there's no charge on it when it's in its chemical formula. So if I have a -3 charge on the anion side, what charge do I have to have on the cation side to cancel out that -3? I'm going to have a +3. So what that tells me, since there's only one iron atom, is that that iron is the +3 iron. Now that I know which ion it is, I can name my compound. So I'm going to name it by writing iron, Roman numeral 3, chloride. When you are writing these, you don't have to put parentheses around the Roman numeral. That's just my personal preference. So now we're just looking at the 2 examples we would see with the 2 different iron ions and what those would look like. So you can see iron has 2 different ions, iron 2+ and iron 3+. We just saw the example, iron 3 chloride, where the corresponding chemical formula was FeCl3. Well, what would the chemical formula look like for iron 2? Well, that's right next door. Iron 2 chloride would be FeCl2. Notice we are adding the IDE endings just like we did when we named other ionic compounds. Here are some examples that we're going to work through in class. So we're going to name the compounds shown here with these chemical formulas, and then we're going to take the names and convert those into chemical formulas. So in summary, we have 2 different types of bonds we've talked about, ionic versus covalent. For covalent bonds, we often see metals and nonmetals, but we will also see some examples when a nonmetal and a metalloid are combined. For ionic, there's many more different types. We have a metal and a nonmetal, which is the simplest form, especially if it's a main group metal. We saw metals with polyatomic ions. We can also see 2 polyatomics together, or a polyatomic with a nonmetal. So I'm going to define oxidation numbers. Now, you already know what they are, we just haven't called them oxidation numbers yet. So what oxidation numbers are, the charges that exist on the monatomic ions. So when we said that barium, since it's an alkaline earth metal, it's always going to form a +2 charge. That +2, that's its oxidation number. So it's just the charges on the ions. They're also called oxidation numbers. These are the numbers that each atom fulfills to gain its full octet. And we talked about that when we discussed isoelectronic atoms in Chapter 2. To determine what those charges should be, all you need to know is how many electrons is that particular atom need to gain or lose to have a noble gas configuration. So we've looked at these charges on several occasions. These are the charges of the main group elements that form for every element in that group. The octet rule says that everybody wants 8 electrons. They all want to be a noble gas. Of course, there's always exceptions to that rule, being hydrogen and helium. They can only have a max of 2 electrons. The rest of the atoms on the periodic table of the main group elements want 8. In this diagram, The numbers above are the number of valence electrons of each element on the periodic table. We use these numbers of how many valence electrons they have so that we can figure out how many they would like to lose or gain to become a noble gas state and have a full octet. Alkaline metals like to have an oxidation number of +1, so they like to have a +1 charge. Well, why is this? It's kind of a review from chapter 2. They're a metal, so we know they like to lose electrons. Since the alkaline metals only have one valence electron in their outer shell, they lose that one valence electron to have a full octet. What that means is, notice I have the electron configurations of lithium and sodium pictured here. You can see that in their outer shell, they each have just one electron in that s orbital. So when they lose that one s electron, they now have a noble gas configuration. So looking at this example, the lithium +1 ion will now have the same electron configuration as helium. So both of their electron configurations will be 1s2. Sodium, when it loses that one electron, now has a noble gas electron configuration the same as neon. 1s2, 2s2, 2p6. Notice that it will have 8 electrons in its outer shell. Its outer shell being all the electrons in level 2, period 2. The electrons being these superscripts here. So 2 plus 6 tells me there are 8 electrons. So now sodium is happy. Potassium, the example also shown here. So we're looking at the electrons in the 3 level. Potassium loses one electron. It is now isoelectronic with argon and has the same electron configuration as argon. Alkaline earth metals. Notice all the alkaline earth metals have 2 valence electrons in their outer shell, represented by these 2 electrons in the s orbital. So if they lose those 2 electrons, they now will have 8 and have the same electron configuration as the noble gas in the row above them. Halogens, they are nonmetals, so we're going to see them gain electrons. Why are they gaining electrons? Because they're trying to get 8 electrons. So if you look at their outer shell, in the case of chlorine here, we have 3s2, 3p5, so that would be the outer shell, the level n equals 3 for the principal quantum number of chlorine. The electrons it has are 2 in the s and 5 in the p. That gives me a total of 7 electrons. Well, since chlorine wants 8 electrons, it's going to gain 1 electron to have 8. That means it's happy. So fluorine, when it gains 1, is now isoelectronic with neon because they have the same electron configuration. The same applies for chlorine, bromine, and iodine. They are isoelectronic with the noble gas in the same row. So let's see how this looks. In this example, I have shown a sodium atom. Now a sodium atom has 11 electrons. If you do its electron configuration of a neutral sodium atom, you will count 11 electrons. Now notice this outer shell in pink here has just 1 electron because sodium is an alkali metal and just has 1 electron in its valence outer shell. So what happens is it wants to have a full octet, a full outer shell. So when it loses that 1 electron, notice now the pink shell is gone. Notice also that sodium now has a +1 charge because it lost 1 negatively charged electron. But its outer shell in blue now, if you count those electrons, you'll see that there's 8 on that blue level because it now has a full outer shell. So it has a same electron configuration now as a neon atom. Now let's look at chlorine. So chlorine, in its pink outer shell, has 7 valence electrons when it's neutral. When it gains 1 electron from sodium, for instance, it will now be negatively charged because it gained 1 negative electron, and it now has 8 electrons in its outer shell, the same that argon, the noble gas argon, has. Last but not least, we're going to look at the properties of ionic versus covalent compounds. So ionic compounds are crystalline structures. They're generally solids at room temperatures, and their melting points and boiling points are higher than covalent compounds. This is due to their crystal lattice. There's a lot of stacking with these ions, creating lots of interactions. For example, sodium chloride, also known as table salt, it has a melting point of 801 degrees Celsius. We're going to do a lab on a hydrate, an ionic compound, and we're going to be heating that compound up with a Bunsen burner. The reason we can do this without destroying the compound itself is because of the high melting points of ionic compounds. With solutions of ionic compounds, if they're soluble in water, you'll often see that the ions will separate into the positive and negative cations and anions. This causes solutions of ionic compounds to form electrolytes. And these electrolytic solutions can actually conduct an electric current. And we'll talk about this more in detail in later chapters. Here's a picture of the crystal lattices of ionic compounds. So all of these purple spheres, if this were an ionic compound of sodium chloride, the purple spheres are sodium plus ions. The green spheres are chlorine minus ions. So due to this intricate stacking, it creates a very stable structure, making it very hard to break apart. Case in point, high melting point. Now let's explore the properties of covalent compounds. So covalent compounds can be solid, they can be liquids, they can be gases, combination. So we're looking at compounds that share electrons. The melting points and boiling points are often lower than ionic compounds. Notice an example here, methane, CH4, or carbon tetrahydride if you're naming it systematically, has a melting point of -182, thus making it a gas at room temperature. Note, there are always exceptions though. One of the exceptions for covalent compounds being silicon dioxide, which is quartz, a very hard high melting point solid. If a covalent compound is soluble in water, it does not break apart into ions since they are sharing electrons. There's no transfer, so no ions exist. These are therefore going to form non-electrolytic solutions. They will not conduct electricity. An example of this would be sugar water. Sugar does dissolve in water, but since it's a covalent compound consisting of carbon, hydrogen, and oxygen, you will not see any ions in the solution.